Now, let's look at polygons. What are polygons? A polygon is a flat shape or is a two-dimensional shape which is enclosed, completely enclosed by three or more edges. We don't have a polygon of two edges. Polygons starts from 3 edges, 4 edges, 5 edges, and so forth. Obviously, an example of a polygon, it's a triangle, which we have talked about. Also, quadrilaterals, we've just talked about quadrilaterals, which are polygons, and quadrilaterals are polygons with 4 sides. Triangles are polygons with 3 sides. They are completely enclosed by those sides. Now, we know that if we have 5 sides, we are going to have a polygon which is a pentagon. Now, a polygon with 6 sides is what we call a hexagon. It's either a regular hexagon or just a hexagon. And a regular hexagon has all sides which are equal. Just a hexagon, not all sides are going to be equal. A pentagon as well, if it's regular, all sides are going to be equal. If it's not a regular pentagon, all sides are not going to be equal. Where a pentagon has 5 sides and a hexagon has 6, a heptagon has 7, an octagon has 8, a nonagon has 9, and a decagon has 10 sides. All those can be regular or non-regular. Therefore, I would love us to talk about polygons with the same number of sides. Now, what do I mean by polygons with the same number of edges? Similar, if I have a parallelogram since we know from our explanation that similar polygons must have the same shape but different sizes. As I can see here, these two have different shapes, therefore they are not similar. But we can even look at further on the condition of similarity, because we've got conditions of similarity is that if I have, for an example here, 6x, if I have 4x there, if I have 3x, and I have 2x there. Now we can see that the sides are in proportion, because if I have A, B, C, D there, and have E, F, G, H. Now the two polygons are not similar. Why? Because we've got two conditions of similarity. Sides must be in proportion, corresponding sides must be in proportion, and corresponding angles must be equal. In this case, we have AB over EF or over HG. AB over EF is equals to, we can see that we have BC over FG. We also have DC over HG, which is equals to also AD over, you can see that it's over EH, where our AB, which is 6x over, we've got 6x over 4x. Then that side is going to be 3x over 2x. which is BC over FG. Even the other sides are going to be like that, where we have 3 over 2. Therefore this, because this cancels, this is the same as 3 over 2, 3 over 2, also that. Therefore, sides, corresponding sides, are in the same proportion, are in proportion. But this angle is not equals to that angle there. This angle is not equals to that angle there. Here we know angles are 90. Here we know angles are 90 there in a rectangle. Therefore, since the corresponding angles are not equal, yes, the sides are in proportion. Both conditions must be true for us to say the two are similar. Let's look at another example. If I can have a rectangle that's got the same shape but different sizes, but we can't conclude to say that they are similar, because if I have there these two rectangles are not similar, yes, the corresponding angles in this case are equal. In this case, corresponding angles are equal, but are sides in the same ratio if I've got A, B, C, D there, E, F, G, H. These two rectangles are not similar. Yes, they have the same shape, they've got different sizes, but they are not similar because A over B, AB over EF is not equals to BC over FG. AB is 6x over 5x, which is equals to, obviously here I'm going to have BC, which is 3x over 2x. You can see that here we have, this is not a 6 over 5, 6 over 5 is not equals to 3 over 2. Sides are not in the same proportion, are not in proportion, are not in the same ratio, are not in proportion. So since sides are not in proportion, but angles, angle A is equals to angle E, equals to angle B, equals to angle F, equals to angle C, equals to angle G, D there, equals to angle H, which is equals to 90 degrees. So this angle is equals to that angle. This angle is equals to that angle. This angle is equals to this angle. This angle is equals to that angle, which they're equals to 90. But the two conditions of similarities do not hold. Sides are not in proportion, but corresponding angles are equal. Therefore, the two are not similar. Let's get more examples. I've just shown you now that not all rectangles, not all rectangles are similar, but we can have rectangles which are similar. There, and we have 6x there, 3x there. Can also have 2x there and x. Or I can just remove these 6x. I can remove there and there. Here I'm gonna have a 1. So if I've got 6, the breadth is 3, 2 and 1. Therefore, these two rectangles are similar, but not all rectangles. Not all rectangles are similar. If we look, this divided by that, 6 divided by 2 is equals to 3 divided by 1. This divide by that, this divide by that, we get 3. To show that all corresponding sides are in the same proportion, which is 3 over 1. Now, these two rectangles are similar because sides are in proportion and angles, corresponding angles, are equal. Since corresponding angle, this angle is equals to that angle, this angle is equals to that angle, this angle is equals to this angle, this angle is equals to that angle. Therefore, corresponding angles are equal and corresponding sides are in the same ratio. This over that is 3, this over that is 3, this over that is still 3, this over that is still 3. Therefore, sides are in proportion and corresponding angles are equal. Therefore, the two rectangles are similar. Let's get more examples on similarity. If I have equilateral triangles, two equilateral triangles with 60 degrees there, 60 degrees there, 60 degrees there, and I have another equilateral triangle with 60 degrees there, 60 degrees there, 60 degrees there, and I have a 6 there, and obviously here I'm going to have probably a 12 there, because it's an equilateral triangle. Therefore, you can see an equilateral triangle sides are in proportion, because 12 divided by 6 is equals to 12 divided by 6, which is equals to 12 divided by 6, which is equals to 2. Therefore, sides are in proportion. If I've got A there, B, C, D there, E, F. Corresponding angles are equal. Angle A is equals to angle D, angle C is equals to angle E, is equals to D, E, F, F there. Angle C is equals to angle E, angle F is equals to angle B. Therefore, corresponding angles are equal and sides are in proportion. Therefore, with equilateral triangles, all equilateral triangles are similar. Let's get another example. Right angle triangles. Not all right angle triangles are similar. If I've got a right angle triangle there with a 45 degrees, and I also have another right angle triangle there with a 30 degrees, 90, 60 degrees. Already we can see that corresponding angles are not equal. Therefore, the two are not similar. Even sides are not in proportion, because if I have 1 there, and root 2 there, and if I have there, root 3 there, we know these triangles are special angle triangles. Therefore, you can see even sides are not in proportion. Sides are not in proportion, corresponding sides are not in proportion, and corresponding angles are not equal. Therefore, the two are not similar. But I can have similar right angle. That is why we're saying not all right angle triangles are similar. But we do have a right angle triangle. We do have right angle triangles which are similar. If obviously I've got 30 there, I've got 60 there degrees, I've got Here I'm going to have 2 root 3. Here I'm going to have a 2 there. Here I'm going to have a 4 there. Therefore, the two triangles are similar because sides are in proportion. This over that, which is 4 over 2, is equals to root 2 root 3 over root 3, which is equals to this side, 2 over 1. 4 divided by 2 is 2. This will cancel. We're going to get 2. 2 divided by 1 is 2. Therefore, this over this is 2. This over that, it's still 2. This over that, it's 2. Therefore, sides are in proportion and corresponding angles are equal. Angle A is equals to angle D, angle C is equals to angle E, angle B is equals to angle F. Therefore, the two conditions of similarity holds. Therefore, the two right-angled triangles are similar. Not all right-angled triangles are similar. There are right-angled triangles which are similar. Not all isosceles triangles are similar, but there are isosceles triangles which are similar as long as the corresponding angles are equal and the corresponding sides are in proportion or have the same ratio, the corresponding sides have the same ratio, then we know that the two polygons with the same number of sides, with equal number of sides, if triangles, we are looking at triangles to triangles, your quadrilaterals to quadrilaterals, as long as they've got the same number of sides, then we can compare whether are they similar or not. Your pentagons, we can compare pentagons since they've got 5 sides, so we can compare 2 pentagons. We can compare 2 octagons because they've got the same number of sides. Therefore, once we find that the corresponding sides are in proportion and corresponding angles are equal, then we know that the two are similar. And why are they similar? It is because of one object is an enlargement of another. It means that they've got the same size, sort of the same shape, but different sizes. Now, as an exercise, you can try to check whether are all triangles similar, as I have done with equilateral triangle and right-angled triangles and rectangle. These 3 with stars, I've just told you, I've just explained that equilateral triangles are always similar. Any 2 equilateral triangles, or any 3, or any 4, they are always similar. I've just shown with an example there. I've just shown that not all right-angled triangles are similar. So you can also, as an exercise, check whether is this true, that not all, some are similar, but not all are similar. As an exercise, you can check whether all triangles are similar, all isosceles triangles are similar. You can also check whether all congruent triangles are similar, all parallelograms are similar. With rectangles, I've just done an example on rectangles, which shows that not all rectangles are similar. Some are similar. You can also check whether a rhombus, square, kite, pentagons. You can also check whether regular pentagons, are they similar, or whether pentagons which are not regular, are they similar. Also, regular hexagon and regular octagons are similar. Since with equilateral triangles, all sides are equal. So if I can have another equilateral triangle, therefore sides are going to be in proportion since all sides are equal. Therefore, even with regular hexagon, it means that they are also going to be similar because all sides are equal. If I can have two regular hexagon or two regular octagons, then these two, since they are regular, they've got equal sides. Therefore, the angles between the sides are also equal. The corresponding angles are going to be equal for regular hexagons. Corresponding angles are going to be equal, and corresponding sides are going to be in the same ratio. Even with this one, regular octagons, corresponding sides are going to be in the same proportion, and corresponding angles are going to be equal. You can test these and see whether it is true, because they look like equilateral triangle. That is why equilateral triangles are similar. Even these two are going to be similar since we have checked equilateral triangles. You can we can do examples on this and check which are similar and which are not. But not all of them are going to be similar. Some are going to be similar. Some are not going to be similar. Some are going to be similar, some are not, even there. But please verify that what I'm saying is true. Now, let's explain a little bit about ratio. When four numbers, A, B, C, and D, are such that the ratio between A and B is equal to the ratio between C and D, we say that A, B, C, D are proportional. When four numbers, A, B, C, D, are such that the ratio between the ratio of A and B is equals to the ratio of C and D, then we say that these four numbers are proportional or are in proportion. Now, if we have A over B equals to B over C, we say that B is the mean proportional of A and C. We say that B is the mean proportional of A and B. Now, we know that when this ratio is equals to this ratio, then the four numbers are in proportion. If I can have, for an example, 6, 4, 3, 2. 6, 4, 3, 2. Are these numbers in proportion? Or are these numbers in the same ratio? Let's look at that. If I say this divide by that, 6 divided by 4, is it equals to 3 divided by 2? Yes. 6 divided by 4 is the same as 3 over 2. Why? How many times does 2 goes there? It goes 3 times. How many times does 2 goes there? It goes 2 times, which is equals to 3 over 2. Therefore, 4 over 6 is the same as 3 over 2, which is equals to 3 over 2. Therefore, these numbers 6, 4, 3, 2 are in proportion. Now, if I have AB over CD, which is equals to 2 over 5. This does not mean that AB is equals to 2 centimeters. It also does not mean that CD is equals to 5 centimeters. AB over CD equals to 2 over 5. We most work with the simplest ratio of equivalence fractions. AB over CD can also be AB over CD. This can also be written as 10 over 25. Why? Because if I multiply this by 5, I get 10. I multiply this by the same number, 5, I get 25. Therefore, this is the simplest ratio, is the simplest fraction of this. This is the simplest fraction of that. Therefore, we normally write the ratio in its simplest form. This does not mean that AP is equals to 2 centimeters and 5 centimeters. It could also mean that AP is equals to 10 meters. It could also mean that CT is equals to 25 meters. Also, AB over CT, if we have that, it can also mean that we've got 6 kilometers over 15 kilometers. Since I've multiplied that by 2, by 3, I multiply that by 3. Therefore, it's in its simplest form, or this, it's in its simplest form. Therefore, AP over CT does not mean that AP is equals to 2 centimeter or is equals to 5 centimeter. It can mean that AP is equals to 10 meters. It can also mean that CT is equal to 25 meters. Or it can also mean that AB is 6 kilometers or CT is 15 kilometers. Therefore, ratio does not tell the length of AB, does not give the length of AP and CT, but it just gives the relative length of AP and CT. Ratio, we write it in its simplest form, and it gives the relative length of a side. It does not give the actual length of the side. That is why we say this could mean 2 centimeters, it could mean 10 centimeters, it could mean 6. 5, it could mean 25, it could mean 15. But we wrote these in their simplest form. So your ratio does not give the actual length. Now, as I've just said, that ratio does not give the exact length. It does not give the actual length. Now, ratio also does not give the units of measurement. That is why I said it could be 2 centimeters, it could be 5 centimeters, or it could be 2 meters, or it could be 5 meters, or it could be 2 kilometers, or it could be 5 kilometers. Therefore, ratio does not give the unit of measurement. It does not give the actual length. It means that we can even remove that. It does not give the units. It does not. Ratio, the unit of measurement, it does not. We don't know whether we're in kilometers or centimeters and so forth. Therefore, ratio does not give the actual length. It does not tell also the unit of measurement, that if we are having 2 over 5, we don't know whether we are in kilometers or meters or centimeters. Now, I want us to look at proportionality in triangles. Before I can start with proportionality in triangles, I just want to explain some property about the area of a triangle. For any triangle, for us to find the area of any triangle, we need the height, we also need the base. If we have the height and the base, then we know that we can find the area of a triangle. For example, if I have an isosceles triangle like that, or not an isosceles triangle, it can be any triangle where if I have the height as I've constructed, which is perpendicular to the base, therefore I can find the area of this triangle, because I have the height, I also have the base. And the base is always perpendicular to the height. As I am standing here, the floor is the base because I am perpendicular to the floor. Therefore, my height obviously is perpendicular to the floor. Therefore, the floor is the base. Therefore, if for any triangle that I can be given, for example, if I can have an obtuse angled triangle, like that. If I want to find the area of this triangle, I know that I need to have height and the base. There's my height of this triangle there. There's my base here. Therefore, once I have the height and the base, I can use the area formula. Area of triangle is equals to half base times height. If I have the base and the height, I can find the area of any triangle. If I've got the base and the height, height there, base there, height there, I can find the area, which is half base times height of this triangle. Therefore, it will depend on whether your obtuse angle triangle, your height can be constructed outside the triangle. If you are an isosceles triangle or you are an acute angled triangle, we can construct the height inside the triangle. Then we know that is going to be perpendicular to the base. Here we construct it outside in an obtuse angled triangle. We construct height outside, which is going to be perpendicular to this base there. Therefore, we can find the area of any triangle that we are looking for. Now, let's look at proportionality in triangles. Two triangles with the same height, but obviously different bases. If they've got the same height, then these two triangles, their areas are proportional to their base. Since these two, we have just explained what do we mean by proportion. It means that we are having the same ratio. Therefore, if we've got two triangles with the same height, these two triangles with the same height, their areas, the area of this triangle over the area of this triangle is going to be equals to this base over that base there. So it means that when two triangles have equal heights, their areas are in proportion with the base. What do we mean by that? Let's write that. It means that the area of triangle ABC is equals to the area of triangle ABC is equals to half base is BC times our height is H over area of triangle PQR is equals to area of triangle ABC over the area of triangle PQR is equals to half base times height, which is the area of triangle ABC, over half the area of triangle PQR. Obviously, our base is that, which is QR, times height. Since the two triangles are inside two parallel lines, they are between two parallel lines. Since these two triangles are between two parallel lines, it means that they have the same height. And since they have the same height, then their areas will be in the same ratio with their bases. Will be in the same, their areas, the area of this triangle over the area of this triangle will be equals to this base over that base. So it means that their areas are proportional to the bases. Therefore, this is equals to this cancels. Therefore, we have BC over QR. Why is that? Because they have same height. Now, if two triangles have equal bases, then their areas are proportional to their heights. In this case, our heights are not the same, but our bases are the same. If our bases are the same and heights are not the same, the area of this triangle over the area of this triangle is going to be proportional to the heights. Therefore, let's write that for this one here. Therefore, the area of triangle KLM is equals to half, obviously, because the area of a triangle is half base times height, half LM base, which is LM, half base, times our height, which is our H. Therefore, over area of triangle KLM over area of triangle XYZ, which is equals to half our base is YZ times our height here in this triangle is K. Therefore, this is equals to H over K. Why is that? Because equal bases. LM is equals to YZ. Therefore, that is why they cancel, and also these cancel. We are left with H over K. Therefore, the area of triangle, the area of this triangle over the area of this triangle is equals to the height of this triangle over the height of the triangle. Therefore, the areas here are in proportion to the base, since the heights are the same. Here, since the bases are the same here, therefore, the areas of these triangles are in proportion with the height. Therefore, the area of this over the area of that is going to be equals to this height over that height. Now, when two triangles have the same base, also having the same height, when two triangles have the same base and the same height, then it means that their areas are equal. Let's see what do we mean by that? That when two triangles are between two parallel lines, therefore, it means that they've got the same height, and if they've got the same base, then it means that the area of triangle DEF is equals to the area of triangle KEF. Since they've got the same height and they've got the same base, then the two areas of these triangles are equal. Let's see that. We know that area of triangle DEF is equals to half our base here is EF times our height for triangle DEF is H times H over the area of triangle KEF. KEF. Area of triangle DEF over the area of triangle KEF, with the area of triangle KEF, obviously the base is still EF, half EF times our height, it's still H. Therefore, this becomes 1 because this cancels, this cancels, this cancels. This becomes 1. This means that we have, I'm just going to write this here. This means that area, I'm just going to write it here. This means that area of triangle DEF over the area of triangle KEF is equals to 1. That's what this means. Since these have cancelled, this is equals to 1. But this one, I can write it as over 1. Cross multiplying tells us that the two triangles have the same area. If I can remove here, the two triangles have the same area. This multiplied by this is going to be area of triangle DEF, which is equals to this times that equals to area of triangle KEF. This just simply means that if two triangles have the same base and the same height, it means that their areas are equal. How did we get that? We've used the proportionality of triangles, where we used the areas which are in proportion to their base and the height, which the height is equal and the base is equal. Therefore, that is why we have area of triangle DEF over the area of triangle KEF is equals to 1 in this case. If it is equals to 1, it just simply means that the area of this triangle is equals to the area of that triangle. What we are saying is that if we've got two triangles which have the same height, then their areas are proportional to their bases. When two triangles have equal bases, then their areas are in proportion with their heights. When two triangles have the same base and have the same height, it means that their areas are equal.